Spatial separation of magnetic atoms in an inhomogeneous magnetic field. An aqueous solution at room temperature contains a small concentration of magnetic atoms, each of which has a spin 1/2 and magnetic moment μ0. The solution is placed in an external magnetic field. The magnitude of this field is inhomogeneous over the volume of the solution. To be specific, the z component of B field is a uniformly increasing function of z. Assuming a value b1 at the bottom of the solution, z equals z1, and a larger value b2 at the top of the solution, z equals z2. Let n plus z dz denote the mean number of magnetic atoms whose magnetic moments points along the z direction and which are located between z and z plus dz. What is the ratio n plus at z2 to n plus at z1? Okay, so you can see here we have an aqueous solution. Between z equals z1 and z2 we have a magnetic field that is increasing linearly with distance from the bottom, and it assumes the value b1 at the bottom and b2 at the top, and we're wondering what is the ratio of n plus z2 to n plus z1, the mean number of magnetic atoms whose moments point along the field direction. So magnetic moment, so for plus we need to have magnetic moment of μ0, and the corresponding energy is for each moment minus μ0b. And the probability of occupancy of this energy level according to our canonical distribution is a constant c times e to the beta μ0b, and the concentration of particles at the point z will be proportional to the probability of occupancy at that level, p plus. So we can write the ratio of the concentrations, mean number of magnetic atoms in the at z equals z2, that is pointing up, divided by at z equals z1. We have the first one is proportional to e to the beta μ0. The value of the magnetic field at z2 is b2. And in the denominator I have e to the beta μ0 b1. That is the value of the magnetic field at z equals z1. So these two will cancel, and I will be left with a ratio n plus z2 divided by n plus z1 must be equal to I don't need the division here, so this is going to be exponential beta μ0 b2 minus b1. So we expect more magnetic moments pointing along the z direction in the position z equals z2 because the magnetic field is simply stronger at that position. So the energy requirements basically tell me that there should be more of them at this point. So this answers the question in part A. Part B, let nz dz denote the total mean number of magnetic atoms. Okay, so total mean number of magnetic atoms of both directions of spin orientation, located between z and z plus dz. What is the ratio n at z2 to n at z1? Is it less than, equal to, or greater than unity? Okay, so let's take a look at the total number. We already know n plus, but we should know n minus. So we know that n plus is proportional to e to the beta μ0b, but n minus, when the magnetic moment points down, it will be proportional to e to the minus beta mu 0b. So because for minus, mu is equal to minus mu 0, the energy is equal to plus mu 0b. For plus, it was plus mu 0, energy is minus mu 0 b, and the Boltzmann factor would be e to the plus beta mu 0b. Okay, so we're looking for total number, n plus and n minus. So this will be proportional to e to the beta mu 0b plus e to the minus beta mu 0b. So if I want to calculate the ratio of the total magnetic moments at position Z2 to Z1, this will be the ratio of the two probabilities, e to the beta mu 0, now at z equals Z2, magnetic field is B2, plus e to the minus beta mu 0 B2, divided by e to the beta mu 0 B1, plus e to the minus beta mu 0 B1. So e to the x plus e to the minus x over 2 is cosine hyperbolic. So if I divide the top and bottom by 2, I see that this can be simply written as cosine hyperbolic beta mu 0 b2 divided by cosine hyperbolic beta mu 0 b1. So this would be our answer for the ratio of total magnetic moments at Z2 to Z1. Let's look at part C. Make use of the fact that, okay, is this greater than 1 or less than 1? Well, because the B2 is greater than B1, we expect that n of Z2 is greater than n of Z1. More moments will be pointing in the plus the Z direction. So if you look at the values here, cosine hyperbolic beta mu 0 b2 greater than or equal to or less than cosine hyperbolic beta mu 0 b1. So b2 is greater than b1, so we should find that cosine hyperbolic beta mu 0 b2 is greater than beta mu 0 b1. So can I see this in a simple way? So let me see cosine hyperbolic x e to the x plus e to the minus x over 2. So let's assume that b2 is much greater than b1. Then I will have this ratio. So the cosine hyperbolic, for example, I can set b1 to 0 and b2 to infinity. So let's see what happens in this case. Well, if b2 is infinity, you will have e to the minus infinity going to 0. Cosine hyperbolic x at x goes to infinity is going to become infinite. And cosine hyperbolic x as x goes to 0 will become e to the 0 plus e to the minus 0 over 2, which is 1. So we find that indeed this implies, I check this limit here, this one is greater than, the numerator is greater than the denominator. Therefore, the answer is the ratio is greater than 1. So this is what we will find. Now let me move on to part C of the problem. Mu 0b is much less than kt, so we will use this to simplify the answers. Okay, so part A answer was n plus z2 divided by n plus z1 is e to the beta mu 0 b2 divided by e to the beta mu 0 b1, and I know that e to the x for x much less than 1 is approximately 1 plus x squared over 2 factorial, etc. So if I use the first approximation here, this would be, the ratio would give me here e to the beta mu 0 b2 minus b1, and assume that beta mu 0 b2 minus b1 is much less than 1, or mu 0 b2 minus b1 is much less than kt. This would give me, for the ratio n plus z2 to n plus z1, 1 plus beta mu 0 b2 minus b1. So this could be an approximate answer in this regime, which is typically true. So and as for the answer for the part B, if I look at the ratio n z2 divided by n z1, so for the top part I have e to the beta mu 0 b2. So let me write three terms here. So let's see what happens. 1 plus beta mu 0 b2, or if I write two terms, you can see that the magnetic field dependence will disappear and I will get a 1. So let me use the third order term, 1 over 2 mu 0 b2 beta square, and 1 minus beta mu 0 b2 plus 1 over 2 beta mu 0 b2 squared. This is for the top, and for the bottom I have 1 plus beta mu 0 b1 plus 1 over 2 beta mu 0 b1 squared plus 1 minus beta mu 0 b1 plus 1 over 2 beta mu 0 b1 squared. So you can see that the beta mu 0 b2s will cancel and beta mu 0 b1s will cancel, and I will be left with the following answer. So let me continue. The ratio n of z2 to n of z1 will be approximately 2 plus beta mu 0 b2 square divided by 2 plus beta mu 0 b1 square. So this one I can write as, if I take it into one parentheses, two parentheses, 1 plus 1 half beta mu 0 b2 square multiplied with 1 plus 1 half beta mu 0 b1 squared to the power minus 1. And here I have, in the second term, if you have 1 plus x to the n for x much less than 1, this is approximately given as 1 plus nx for the Taylor series expansion. So I can use that here. So this applies to the second term here. So this is a further simplification I can have. So I'm using this for this term, and this is going to give me n of z2 divided by n of z1. If I want to simplify this further, this will be 1 plus 1 over 2 beta mu 0 b2 squared multiplied with 1 minus 1 over 2 beta mu 0 b1 squared. So I can continue this calculation for the ratio n of z2 and of z1. I will have the first term 1 plus so let's see, 1 minus 1 over 2 beta mu 0 b1 squared plus 1 over 2 beta mu 0 b2 squared, and then I will have minus 1 over 4 beta to the fourth power mu 0 to the fourth power b1 square b2 square. So since I'm assuming that mu 0 b over kt is much less than 1, this squared term can be neglected, so it's too small. So I would be left with the following approximate result: n of z2 and of z1 is approximately 1 plus 1 half beta mu 0 square, which is mu 0 divided by kt squared, and then I would have b2 squared minus b1 squared. So let's check the math here. So we have 1 plus 1 minus 1 over 2 mu 0 b1 squared plus 1 over 2 mu 0 bt squared minus 1 over 4 mu 0 to 4 beta to 4 b1 squared b2 squared. That term becomes 0. So then we have 1 plus 1 half beta mu 0 squared parentheses b2 square minus b1 square. So we can give this as our approximate answer in this limit. You can see that this ratio is greater than 1. N of z2 over n over z1 is greater than 1 if b2 is greater than b1. So just as we expected, as we have found out in part B. Okay. So in part D of the problem, let's give some numerical values. Estimate the magnitude at room temperature. Mu 0 is 10 to minus 23 joules per Tesla, B1 is 0, B2 is 5 Tesla. So let's give these numerical values. So first of all, I have B1 equals to 0 here. On the other hand, I have for mu 0 b2 over kt, this will be 10 to minus 23 joules per Tesla times 5 Tesla divided by the value of kt at room temperature is 1 over 40 electron volts. So 1 over 40 times 1.6 10 to minus 19 coulombs to convert it into joules, and this gives us 0.0125. So if you look at the ratio n of z2 divided by n of z1, if I have cosine hyperbolic 0.0125 divided by cosine hyperbolic 0, this will give me 1.000078. And also note that if I calculate this using my approximate expression, 1 plus 1 over 2 mu 0 b2 over kt square, which is 5 times 10 to minus 23 over 1 over 40, 1.6 10 to minus 19 squared. This also gives me 1.000078, approximately the same answer. So basically, by putting some numerical values here, I have checked and found that my approximation was correct in this limit when I have beta mu 0 b is much less than 1. I indeed have this approximation valid. So this would be my answer for the ratio with these numbers. Now, we have an aqueous solution. We have an inhomogeneous distribution of magnetic atoms. They each have magnetic moment mu 0. The magnetic field is inhomogeneous. It varies as a function of z, linearly increasing function of c. Minimum value at the bottom, z equals z1, b is b1. And maximum value at the top, z equals z2, b equals b2. First, we calculated the ratio of the mean number of magnetic atoms whose magnetic moments point along the z direction located between z and z plus dz for the position z equals z2 and for the position z equals z1. So the magnetic moment is pointing up, the energy is minus mu 0b, Boltzmann factor is e to the beta mu 0b, and the concentration, the mean number of atoms is proportional to the probability of occupancy of the energy level. So we have the ratio e to the beta mu 0b2 over e to the beta mu 0b1. On the other hand, when we calculate the total mean number of magnetic atoms of both directions, we have to consider n plus and n minus, and then we have the ratio of e to the beta mu 0b2 plus e to the minus beta mu 0b2 divided by e to the beta mu 0b1 plus e to the minus beta mu 0b1, which gives us a cosine hyperbolic ratio. And cosine hyperbolic of something divided by cosine hyperbolic of something smaller is greater than 1. So I have checked this in the extreme limit when b2 is much greater than b1. I've set b2 equals infinite, b1 equals 0. I find that the cosine hyperbolic is increasing as a function of x, so this ratio is greater than 1. When I look at the answers to part A and B, when the beta mu 0b value is much less than kt, I find that my approximate answer is 1 plus beta mu 0b2 minus b1 for n plus ratios, and it is 1 plus 1 half beta mu 0 square b2 square minus b1 square in the total mean moment calculation. And when I give some numerical values for n of z2 to n of z1, I find that it is 1.000078. First of all, I have checked that my approximation was correct in part C, which was verified. And second, I see that this ratio is greater than 1, which was something that I have argued in part B. I numerically find that this is the case for the specific numbers given in the problem.